Hello again, and welcome back to C++ Real-Time Audio Programming with Bela. The topic of today's lecture is latency. We talked at the beginning of this series about how Bela is an ultra-low latency audio platform, which can achieve as low as 1 millisecond round-trip latency. In today's lecture, we'll look further at what we mean by latency and why it matters for our code. We'll look at the main sources of latency and how we can measure it. In the course of this lecture, you'll see how to measure the latency of an audio system using a benchtop oscilloscope, and we'll also make an automatic latency tester that runs on Bela to report the latency of external audio devices. As always, you can find the companion materials on GitHub at the link at the bottom of the screen. As usual, you'll need a Bela starter kit or a Bela mini starter kit to run the code examples. This is one of the few lectures in the series where it will also be helpful to have a benchtop oscilloscope and function generator. If you don't have these things, that's fine. You can still follow along with the example I show you. After we use the benchtop oscilloscope, we'll go on to build a latency tester that runs entirely on Bela without needing any outboard hardware. To use that example, the only thing you'll need is a 3.5mm stereo audio cable. Okay then, let's start with a review of block-based audio processing. Recall from the earliest lectures in this series that the reason that we process audio in blocks is that our computer may be occupied with a number of different processes running at the same time, and we can't guarantee that our audio code is going to be able to run in time to produce each audio sample as it's needed. So what we do instead is we have the hardware aggregate together a number of audio samples and pass that block into our audio callback function, which in the case of Bela is the function called render. A typical block size might range anywhere from 2 samples on Bela up through hundreds of samples or more on a general-purpose operating system. The default block size for Bela is 16. The way it works then is every time the audio hardware is playing back one block of samples, our code is busy calculating the next one to make sure that it's ready on time, like this. Each block, of course, being comprised of several samples. There are a number of advantages of this arrangement, the main one being that we need to call our audio code less often, which allows us to tolerate more timing uncertainty, and the larger the block size we choose, the more timing variation we're able to deal with. But there is also a disadvantage, and you can probably guess what it is based on the title of this lecture. The disadvantage is latency. Specifically, the larger the block size we use, the more latency we're going to end up with. We'll talk about this in a moment. Let's first define our terms. Latency is defined as the delay between action and reaction, which is a fundamental property of most digital systems. So in this example, if we have a sensor which we are responding to generate an audio output, then the delay between when the sensor signal arrives and when the audio signal is generated is our latency. This is typically measured in some number of milliseconds. There are several sources of latency in a digital audio system. One of them comes from the audio converters themselves. The physical parts we use to convert audio from analog to digital and back again are what's known as sigma-delta converters. The advantage of the sigma-delta converter is that it can achieve a very high bit depth and excellent noise performance using relatively inexpensive hardware. The price we pay for that is that these converters involve an internal digital filter which is doing something called noise shaping. This digital filter adds a latency which is entirely internal to the part itself and has nothing to do with what operating system we're running on or what our block sizes are. In a typical system, we might see a latency anywhere from around 500 microseconds to 1 millisecond round trip from these converters. But the biggest source of latency in most digital audio systems comes from the buffering. This is the process that we talked about a moment ago. It typically happens in the operating system and the audio driver before our audio processing callback is ever even called. The amount of latency here depends directly on the audio block size and might range anywhere from 1 to several dozen milliseconds. Finally, it's important to remember that our audio code itself can generate latency. Every filter, whether analog or digital, generates what's called group delay, which we'll talk about in a moment. This is a mathematical property of the filter that has nothing to do with how fast or how slow our processor is. There are also certain classes of audio processing that are particularly notorious in terms of adding latency. One of these is block-based audio processing, for example based on fast Fourier transforms. We'll talk more about how to create systems like this in a later lecture. Each of these sources of latency applies to a simple digital audio system that has only an audio input and audio output. Things become a little bit more complex when we talk about interactive systems, where we might want to use other inputs besides audio to control sound synthesis. In particular, if we have the common configuration of using a sensor board like an Arduino connected to a computer doing the audio synthesis, then we incur a number of different sources of latency. One of these sources of latency has to do with how fast we sample the sensors. Essentially, we might expect up to 1 sampling period of latency just due to the sample rate of the sensors. We also incur some latency from the communication from the sensor board to the computer. At a hardware level, the USB full-speed communication protocol transmits data in 1 millisecond frames, so we might expect a small amount of latency here. If we're dealing with other serial interfaces, for example traditional MIDI ports, then we might also have latency there on account of the bit rate of the communication. For example, one 3-byte MIDI message takes around 1 millisecond to transmit. But one of the biggest sources of latency, as before, is in the operating system itself. Typically speaking, USB serial drivers are not optimized for speed, they're optimized not to lose any data. What this means is that when we have data coming in over USB, we can't guarantee that our code will be called right away to deal with it, and we might end up with a highly variable and unpredictable amount of latency. Finally then, if we're generating sound, then we have at least half of the audio chain we saw in the previous slide. All of these sources of latency can really add up, but for Bela, the good news is that we can avoid a number of parts of it. Particularly, we can avoid any communication latency since the audio and the sensor processing are done on the same board, and we can also avoid most of the driver latency because of Bela's hard real-time environment, which treats analog and digital signals just like audio signals. Treating analog and digital I/Os like audio signals also helps us avoid another common problem, which is jitter. It's quite common when you have a sensor board and a computer generating audio that the action-to-sound latency might vary randomly from one event to the next. This is because the audio and sensors tend to be handled on different threads. What we end up with is a situation like this. If the audio is being processed in blocks, and we have triggers from our sensor data coming in at different times, typically speaking, it's hard for the audio code to reconstruct precisely when that trigger arrived. So what it does in response is it simply generates the response to the trigger at the beginning of the next audio block. As a result, the timing between the trigger and the resulting sound might vary randomly from one event to the next, and this random variation is what's called the jitter. And you may be able to see from this plot why having a larger audio block size could result in more jitter. Here's a practical real-world example of this. We took an Arduino microcontroller board and we attached it by USB to a computer, which was running Max MSP to generate sound. We had a reasonably fast serial communication and a 44 kHz audio sample rate with a reasonably small block size. And we built a jig which took 1,000 successive measurements of the latency between a trigger and the sound response. Plotting these on a histogram, we can see that each result falls into one of just a few bins, and that the bins are separated from one another by intervals of the audio block size. Now you might reasonably ask, does any of this latency and jitter stuff even matter? The answer is an emphatic yes. Latency Latency has an extremely important effect on the perceived quality of audio and interactive systems. For a long enough latency, we might actually hear an audible delay between the input and output. But what's interesting is that even an imperceptible delay that we don't recognize might make a system feel less responsive to us, and this is particularly a problem when we're dealing with digital musical instruments. So what's a reasonable guideline then? Well, back in 2002, David Wessel and Matthew Wright proposed that digital instruments should have a latency no more than 10 milliseconds, with a jitter of no more than 1 millisecond. In our own research at Queen Mary, we conducted a controlled experiment of this, and we found that yes, in fact, 10 milliseconds of latency, if there is no jitter, seems to be about as good as no latency, but 20 milliseconds of latency, or 10 milliseconds of latency with 3 milliseconds of jitter, rated far worse, even when the players couldn't recognize an audible delay. The takeaway message from all of this is that we should always strive to keep our latency as low as possible, and because some sources of latency in our audio code are unavoidable, then we should minimize the ones that we do have control over. Let's now return to each of the sources of latency in more detail. First, we'll look at the latency inherent to the audio converters. In the ideal case, we would have an instantaneous conversion from continuous to discrete time and back, according to these sampling equations here. In practice, our ADCs and DACs introduce a latency because of the sigma-delta modulation that they use and the built-in digital filters that are used in the sigma-delta process. To re-emphasize, this is a latency that does not depend on the processor or the operating system in any way. So we might reasonably ask, how do we find how much latency this is? Where do we find the specifications? Well, the answer, as always, is that we go look at the datasheet. Here's the datasheet for the audio codec that's used on Bela. We can see here some parameters for the digital interpolation filter used on the DAC. And we can look in particular at the parameter called group delay. We can see that it's measured as 21 divided by fs seconds. What this means is that the DAC introduces 21 samples of latency, and that the amount of time in seconds this corresponds to will depend on the sample rate. In the case of 44 kHz, this latency would be 476 microseconds. We could look at the same thing for the analog to digital converter. We see that this filter introduces 17 samples of latency, which at 44 kHz is 385 microseconds. Therefore, our round-trip latency will be around 850 microseconds or so. Next, let's look at the latency introduced by buffering. This is typically our most significant source of latency, and it can also be one of the more complex ones to understand. It affects both the input and the output, so let's look at these in turn. On the input side, we should ask how we create the block of samples that's passed to our render function. What we do is that we wait until we have enough samples gathered together into an array. Once those samples are gathered, then we can pass it to our render function. Then on the output side, we need to consider how we play back a block that was calculated in our render function. What'll happen is that our render function will return an entire block of samples, which then needs to be played. So how long will it be until the last of those samples is played? Well, the answer is for a block size of n, it will take n samples until the last of the samples is sent to the hardware, like this. You can see here that it would take 16 samples before the playback reaches the end of this block. Therefore, let's consider the best possible case for buffering latency, which is a straight-up pass-through. As soon as our block is received, we immediately send it back out to the hardware. It would work approximately like this. So we have our block of samples that's gathered from the ADC. Once that block is complete, it's sent back to the DAC immediately, which plays it back. The question is how much latency this incurs. In this case, we incur one block length of delay, because as soon as we've read the last input sample, we can immediately start playing the first output sample. So for example, if our buffer size was 128 samples, our delay would be 128 samples, or about 2.9 milliseconds at 44 kilohertz. However, there's a practical problem with that simple example, and what might that be? Well, the question is, when are we supposed to do our processing? We might wait until the input block is totally finished and ready, but the problem there is that we have to react instantly if we plan to send that block back to the DAC right away. This is exactly what we are trying to avoid by having a block-based system. We need time for our computation to take place. Therefore, what we're going to do is we're going to add an extra buffer of delay, specifically to give the processor time to do whatever our audio calculations are going to be. Therefore, we find ourselves in a situation where there are three things going on at any given time. We have our audio input hardware, which gathers samples together into a buffer. Once that buffer is full, we pass it to our render function, which can do the audio calculation while the next block of samples fills up. Once that's done, we pass it to the audio output hardware, which plays back the block. So notice that at any given time, there are three blocks of audio in process, one of them being filled up at the input, one processing in render, and one being played back at the output. And the result is that the total latency from input to output is always going to be twice the buffer length, and this process can continue indefinitely. So in this architecture, we have one buffer length in which to do our audio processing. The question is what happens if we miss that deadline and we take too long to compute it? The answer is that we run out of data, we have nothing to send to our DAC, and we end up with what's known as a buffer underrun. This manifests as an undesirable gap or click in the audio output. On the other hand, if we have audio input data coming in faster than we can process it, we have a similar problem. We might end up with what's called a buffer overrun and end up losing some of this input data because we can't process it fast enough. Because the audio input and output typically share the same clock and buffering structure, you'll oftentimes hear these conditions together called a buffer underrun or sometimes an X-run. Now, on the other hand, what happens if we're lucky enough to finish our output sooner than we expected? Is this okay? In this case, we're fine. Nothing different happens. We're going to play our output back at exactly the same time as we did before. In an early lecture, we used the analogy of the assembly line to talk about real-time audio processing. If you're working on an assembly line and you finish your task before the line moves on, you don't get any special benefit from that because you still have to wait for the next progression of the line before you can start your next task. And that's the way it is in audio processing as well. On the other hand, our system is probably doing more things than just audio, so releasing the CPU to do other tasks will certainly be useful for other reasons. A few further considerations about underruns. Hard real-time systems like Bela should not generate underruns, at least not because of what else is running on the board. Your audio code could always be too slow to run in real time, and then you'd end up with an underrun, but the system architecture of a hard real-time system should be able to guarantee you some level of responsiveness. On non-hard real-time systems, underruns usually have to do with unpredictable delays in the operating system because of other processes running on the computer. In this case, the question is why should we choose a larger buffer size? The reason for this is that we can handle more timing uncertainty. For example, here, if the arrows show you when our audio processing finishes, you can see that we end up with an underrun here where the processing wasn't done by the end of the block. But if the blocks were twice as long, we might have been able to handle that timing uncertainty more effectively. Finally, let's talk about the latency introduced by audio processing itself, typically known as group delay. Except for a trivial gain control, every filter, whether analog or digital, will introduce some amount of group delay, and we'll consider specifically here our familiar LTI filters that are commonly encountered in DSP. We'll start with the simple case of finite impulse response filters with symmetrical coefficients. DSP theory tells us that the group delay of these filters is a constant with respect to frequency. Every frequency will be delayed by the same amount, which is m-1 over 2, where m is the length of the filter. This class of filters is known as linear phase because a constant delay with respect to frequency translates to a linear phase shift with respect to frequency, as we see in the green plot in the middle. More generally, we might ask how the phase response of a filter relates to its group delay. Again, we can find the answer in signal processing theory, which is that group delay is defined to be the negative derivative of the phase with respect to the frequency. In other words, wherever the phase is changing quickly with respect to frequency, those are the frequency components that will have a large group delay on them. And we can see here that this definition is consistent with our idea of linear phase filters from the previous slide, because the derivative of a linear function is a constant value. Now, it's important to emphasize that this quality of linear phase is never true of IIR filters. With IIR filters, which includes all the types of filters that emulate analog circuits, we'll always have the highest group delay around the cutoff or center frequency, because this is the place where the phase is changing the most rapidly. Here we can see an example of a second-order Butterworth filter. On the left we see the magnitude response in blue and the phase response in green, and on the right we see the group delay measured in samples. We can see that there's a modest peak in the group delay right around the cutoff frequency of the filter. But if we now look at an eighth-order filter, we can see that the group delay is considerably higher overall and with a more concentrated peak than it was for the second-order filter. The same thing happens if we increase the Q of our filters. A place where this might particularly matter would be in a loudspeaker crossover, where we might have a woofer and a tweeter and some frequency where the signal transitions from one driver to the other. A group delay with a very high peak might delay certain frequency components more than others. This might smear the signal in the time domain, and it could also lead to phase misalignment between the woofer and the tweeter. The point, then, is that we can never remove group delay entirely. It's a mathematical property of our filters that has nothing to do with the processing time. However, we can design our filters to achieve different parameters of this delay. Okay, so as a final check, what would be the group delay for a 1-second delay effect? Well, trivially speaking, the answer is that the group delay is 1 second. But then the question is, how would you represent this as an FIR filter at 44 kHz? You need to have at least 44,100 coefficients, with the last of them having a value of 1 and all previous coefficients having a value of 0. That's a summary of latency and where it comes from. Now let's look at how we can measure it. The easiest way to do this is to run a simple pass-through project on Bela, which copies the audio input to the audio output unchanged. Then we're going to use an oscilloscope and a function generator on our lab bench to measure the delay between input and output. If you have a scope and a function generator, then you can follow along on your own board. What you need to do is go to the Bela IDE, go to the tab for the examples, look in the category called Fundamentals, and then you need to open the project called Pass-Through. As you'll see here, the render function just copies the audio inputs into the audio outputs, and it does the same thing with the analog inputs and the analog outputs. Going back then to our test setup, what we're going to do is use the function generator to create a signal with really obvious edges. We're going to pass that signal through the Bela board, and we'll use two different channels of the oscilloscope to measure the input signal and the output signal. The difference between them in time will give us our latency. The steps we'll follow is to connect the function generator to the Bela audio input. To do this, you'll either need a 3.5mm audio cable with wires on the other end, or you'll need specialized socket wires that you can put over the pins of the Bela audio connectors. You might find it convenient to use a breadboard to connect both the function generator and the scope to the Bela audio input. After that, what we need to do is hook up the oscilloscope. If you don't use a breadboard, another option is to use specialized BNC cables, including a T adapter, to connect your function generator directly to the scope input as well as to your Bela board. Finally, you should connect the Bela audio output to channel 2 of the oscilloscope. Let's look at these things in practice now. Okay, so here's the probe for channel 1, and we're going to connect the ground lead of the probe to this wire here. And we will connect that to the ground on the Bela board, like so. And we will connect the probe tip to the left channel of the audio input, which is the middle of these 3 pins, like that. Okay, now we have the probe for channel 2, which we're going to connect to the left pin of the audio output, like so. Then here we have some socket wires which come from our function generator. We have the ground and the signal. These need to be connected to the audio input. So we have the ground lead here on the left and the audio input in the middle, like that. Then here are the alligator clip leads, which come from the function generator. We need to connect those through to the socket wires. There's the ground, and there is the signal. Okay. What we'll do after we wire things up is configure our function generator. We need to generate a low-frequency square wave so we have clear edges, but also quite a long delay between each successive edge. I recommend you use a frequency of no more than 50 Hz, and that you use an amplitude of no more than half a volt peak to peak to ensure that we don't have any clipping on the Bela input. Once the Bela program is running, then we'll use the capabilities of the scope to measure the difference in the timing of the edges for the input and the output. So let's have a look at that now. Here we have our oscilloscope. And we have the two probes connected to channel 1 and channel 2. Now this scope has a function generator built into it, and its output is over here on the left. Now we need to turn on the two channels of the scope here, 1 and 2. Now we might need to adjust the voltage ranges of these channels to ensure that we can see the signal clearly on the screen. So here we have it as 500 millivolts per division. We might also have to adjust the position of these so that we can see the waveforms clearly on the screen, like so. Now from here, we should turn on our function generator, which again in this case is built into the oscilloscope. So we press this button, and we will see the waveform appear on channel 1 corresponding to the input. We can see it set to a square wave, to a frequency of 50 Hz. The amplitude is set to half a volt peak to peak, there's no offset, and the duty cycle is 50%. Depending on how you have your scope set up, you might need to adjust the horizontal scale so that we can clearly see the waveform on the screen. So if we adjust that back and forth, we may want to leave it at a setting where we can see one or more periods of the oscillation on the screen, like this. Okay, now we can go back to our Bela program at this point, and we can run the pass-through code. It will build, and once it runs, then we will see the output on the scope, like this. Now you'll notice that there is a bit of sloping on the output waveform. This is nothing in particular to worry about, it's just the high-pass filtering on the Bela audio inputs, and it doesn't matter in the context of measuring the latency. What we're interested in here is the difference in time between the edge of the input signal and the output signal. And we need to measure the amount of time between the two of these. We could do this by reading the number of divisions on the scope, but we could also use the cursor functionality that most scopes provide. So here I have the cursors that I can turn on by pressing this button, and we are going to select cursor X1. And having selected that, I can adjust the cursor position until it lines up with the edge on channel 1, like so. Then what we can do is we can select cursor X2, and we can adjust that one to line up with the edge of the signal on channel 2, like so. Now we might want to zoom in on the horizontal scale so that we can see the edges more clearly, and now we can go back and adjust our cursors more precisely, like that, and then back to X1, we can adjust that until it matches the edge of the waveform. And there we go. We can read off the latency from the screen, which is 1.66 milliseconds. Okay, now what we can do is change the block size in the Bela audio settings from the default block size of 16 down to the smallest block size, which is just 2 audio samples. And we can go back and we can run this program again, and we will see the waveform appear on the scope again. Now, we should adjust the cursors to match up with the new edge of the output channel. So we will select cursor X2, adjust that until it matches the falling edge. And there we have it. A latency of 1 millisecond. For the last part of this lecture, let's look at how we can use Bela itself as a latency tester, either for its own loopback latency or to measure the latency of another audio device. We'll make a C++ project that does this. What we'll do is at regular intervals send a simple pulse with an abrupt onset to the Bela audio output, and then measure how long it takes to come back. So the output will go through some sort of device under test, which could also be just a simple loopback, and it will come into the Bela audio input. And in our code, we'll measure the difference in time between when we started generating the signal and when it came back to us, and this will be our latency. Understanding how to do this builds on what we discussed in the previous lecture. Recall that to generate events with a time delay, we can't use anything like a delay statement in our code or we'd end up with an underrun. Instead, what we have to do is we have to count the elapsed time as we go along so that we know when to start our next event. Instead of using the system clock time, the best way to do this with real-time audio is to count the number of audio samples that have gone by. Because we know the sample rate of the audio, we can convert the number of samples into a number of seconds according to a particular formula, like this. Because it's likely that our events will happen in different calls to render, we want to use a global variable to hold how many samples have gone by so we don't lose track of where we were. Suppose that we wrote this latency tester code and we hook the Bela audio output directly back to its input. How much latency should we expect and why? Well, presumably we should measure the same amount of latency as we just did with our benchtop oscilloscope. That's a good starting point. There will, of course, be some latency in the audio codec as well as some latency in the buffering, as we've discussed. To see how this looks to our C++ code, let's consider the hardware input and output, and also the audio read and audio write functions that we call inside of render. Remember that we'll have a loopback cable attached here, so whatever appears at the audio output is the exact same signal that's going to appear at the audio input, with no inherent delay in hardware. Suppose then that we are running with a block size of 8 samples, and suppose that our latency tester code generated a pulse starting at sample 4 of a particular block. We'll call audio write to write those samples to the output, and they will appear on the audio hardware in the next block. Because the input and output are connected with a loopback cable, the same signal will appear at the audio input. In this particular block, we won't yet be able to read this signal with audio read because it's going to take one more block for it to propagate through. However, in the meantime, we will still be writing more samples to the audio output. So if we go one block further, then now we're writing samples 8 through 15 to the output, which is looped back to the input. Meanwhile, we're generating samples 16 through 23. But now, the input from the previous block has made its way into our audio read function, and you can see that here we're going to be able to finally read that pulse that we first generated at sample 4. In other words, exactly as before, it'll take at least twice the buffer length before what we write with audio write will come back into our audio read function. This example accounts for the latency in the system buffering, but not for the latency in the codec itself. We'll look at that in a moment. Your task then is to build the latency tester project in the companion materials. This is a relatively complex project and most of it is done for you, but there's a few sections which are marked as to do. One of these sections involves counting the number of samples required to initiate a new pulse, and the second of them involves correcting for the latency introduced by the buffering. When you're done and you run the code, you should connect a loopback cable between the audio input and the audio output. The easiest way to do this is with a 3.5mm stereo cable connected to the two audio adapter cables, but you could also make your own loopback with Molex connectors or with socket wires. When you run the code with a loopback attached, the latency measurements you see should be very similar to what we saw on the scope. Pause the video here and try it. Okay, here we have our completed latency tester code. You might have had some time to look through how this works. You can see that we have a number of global variables at the top of the file, which have to do with the timing of the pulses and reading back the audio input. We use the Bela oscilloscope in this example so that we can see the input and the output. And in the setup function, we're going to calculate the interval between successive tests and the length of the pulse that we generate. Inside of render, we have our typical for loop, which counts through the number of audio frames. We're going to start by reading all of the audio inputs, take the absolute value of each one, and then average them all together. That's just to avoid problems with phase inversion or having the channels hooked up incorrectly. The first of the blocks of code you need to create is given to you here. What we're doing is that we're incrementing the global variable gTestCounter. This is counting the number of audio samples that have gone by since the start of the last test, and if it exceeds the test interval calculated inside of setup, then we do a few things. First, we reset the counter back to 0 so that we can start counting from the beginning again. We're also going to check if we were already in the midst of a test and a pulse hadn't come back to the input yet. If that's the case, then let's just print a message to warn that we didn't receive the pulse back. You can see here that we're using a function called rtprintf. rtprintf should always be used inside of render instead of regular printf. Regular printf is not safe for running in hard real-time, and it'll cause a mode switch which may lead to underruns in your audio output. Finally, in this block of code, we just need to set this flag GINTest to be equal to true. By setting this flag to true, we're going to change the behavior of the code right below it. The code that's already given to you is checking whether the input is above some kind of threshold. What we're doing here is called a comparator with hysteresis, and we'll look at that in a later lecture. If we find the input is above the threshold, then we assume that that's our pulse coming back, and what we need to do is measure how much time has gone by since we started generating it. Once we get here, the amount of time that's gone by is going to be given to us in the variable gTestCounter. You can see this down here in the RT_printf statement. It's showing us the amount of latency in milliseconds and also in samples. gTestCounter is going to give us the amount of latency in samples. To convert that to milliseconds, then we need to divide it by the sample rate, and we also need to multiply by 1,000 to get from seconds to milliseconds. Now you can see in this statement that we're giving the latency in milliseconds and in samples, and also the amount of latency that's directly attributable to the hardware. That's what's happening in this statement, which was your second to-do. The variable called normalized samples is going to have subtracted from it the amount of latency that we know is intrinsic in the buffering of Bela. We know the buffer size because we can find it in this variable called audio frames inside of the Bela context. By subtracting twice the number of audio frames, we can end up with only the amount of latency directly attributable to hardware factors, including the codecs themselves. Then finally, at the bottom of render, we have some code for generating a pulse which starts at a value of 1 and decreases linearly toward a value of 0. We'll see more about generating envelopes like this in a later lecture. We have here some code for detecting whether the input is below the threshold, our typical code to write our generated audio to the output and log it to the scope. So in this case, I've hooked up a loopback cable from my audio output back to my audio input, and that lets me run the example. And we can see that the amount of latency that's reported is exactly what we saw when we were measuring it with the oscilloscope, which is great. And we can also see that when we subtract off the amount of latency due to buffering, then we end up with the amount of latency due to hardware of just over 0.9 milliseconds. We can stop this example now, and let's change the audio block size as we did before. So I'm going to change this from 16 samples down to, let's say, 4 samples. And if I run this again, then we'll see that the amount of latency attributable to the hardware is exactly the same as before, 41 samples, but the total amount of latency is now smaller, 1.11 milliseconds. So hopefully this is a useful project because you could test not only Bela's loopback latency, but also any other audio hardware that had both an input and an output. You can also easily adapt this code to use the analog inputs and outputs rather than the audio inputs and outputs. That would essentially require changing every reference to audio read and audio write to analog read and analog write, to change to count the number of analog frames rather than the number of audio frames, and also to remember to use the analog sample rate rather than the audio sample rate. That brings us to the end for this time. As always, don't forget to click subscribe to be notified of new videos as they're posted. You can follow us on social media or drop by our forum, our blog, or our knowledge base for more information. Thanks a lot for following along. See you next time.